our second learning objective there, and what we're trying to do here is that so we gave you a formula, we said, oh, this is magnesium nitrate, and this is copper sulfate, and so on and so forth. How do you come up with those formulas? How do you know it's 1:1 ratio, it's 2:1 ratio in this case? So basically what we're trying to get at is that you need to know the masses of each of the elements involved in 1 mole of any compound so that you can determine the molar ratio. And we are doing this thing backward, actually. Give you the formula, ask you to determine the percent composition for each of the elements. Well, when you have an unknown compound, you may not even know what kind of elements are in there. So you can't come up with a formula. So the process really is that we're supposed to determine the formula first before we know the percent composition of each of the elements in there. And so we just want to give you an idea, how do we determine the relative quantity of each of the elements involved in there? And our next learning objective there will introduce you to determine how we determine the empirical formula, molecular formula. Is we give you, for every compound that we know, we have a formula representing the fixed ratio among the elements involved in there. How do we come up with that? How are those formulas determined? So that's what we're going to be looking at in our next learning objective there. And we have different ways to analyze our sample. Okay, so you can decompose a particular compound into its elemental form. For example, water. You can decompose water back into hydrogen gas and oxygen gas. Okay, so if we don't know the formula of water, and we have a certain amount of water, we can measure the mass of it. Okay, and then we decompose it back into hydrogen gas and oxygen gas, and we can take a look at how much for a fixed amount of water, how much hydrogen gas do we get, how much oxygen gas do we get. Okay. And in the mass of the hydrogen gas versus the mass of the oxygen gas there, we can determine how many moles of hydrogen comes out from the fixed amount of water that you decompose. And do the same thing for the oxygen there. From there, you can determine the molar ratio. Once you get the molar ratio, you get the formula. So in this case, it happens to be every 2 moles of hydrogen with 1 mole of oxygen. So the formula will be H2O. That's how we determine the formula for something as simple as water. So that's what we call the elemental analysis there. Given the elemental analysis in mass or percent composition, and the molar mass of the compound there, we need you to be able to determine, really, calculate the empirical molecular formula for a compound, and also be able to determine the empirical formula from the result of combustion analysis. And sometimes when you burn something, we would have the knowledge of what it becomes. Say, if you burn gasoline, you always get carbon dioxide and water. Now, carbon dioxide, carbon comes from gasoline. Okay, and the water, H2O, hydrogen comes from gasoline. Oxygen, though, oxygen comes from, could be gasoline. Well, we may have oxygen in there, and oxygen can also come from oxygen in the air. So in water, carbon dioxide there. So combustion analysis would be one of the widely used methods to determine the empirical formula or molecular formula for an organic compound. Because most of the time you can burn organic compound and then you can convert it into either carbon dioxide and water, nitrogen dioxide, and so on and so forth. So this is the idea here is that our intention here in this particular learning objective is to introduce a method that we can use in chemical analysis. So again, going back to the definition, what is the empirical formula? What is the molecular formula? And we gave you this definition yesterday when we introduced the chemical formulas. So empirical formula is the formula that gives you the simplest whole number ratio of atoms in a compound. And molecular formula actually is either the same as or a multiple of empirical formula. Okay, and the examples that we use here, H2O. This is the molecular formula and empirical formula for water molecule. Well, H2O2, hydrogen peroxide, and this is the molecular formula, the actual number of atoms in each molecule there. And the empirical formula will be HO. So you can see the relationship between H2O2 versus HO is that if you multiply everything by 2, you get the molecular formula. Okay, so that's why we say molecular formula is either the same as or a multiple of the empirical formula. And this number is the number that we need to determine when we try to come up with the molecular formula. So examples of that, if you have propane, carbon-3, hydrogen 8. Now, the molecular formula may be carbon-3, hydrogen 8, and it could also be carbon-6, hydrogen 16 times 2. And we'll give you that. Times 3, you get carbon-9, hydrogen 24, and so on and so forth. Okay? So if for organic compounds there, and the formula that you come up with may not be the actual molecular formula, and the simplest whole number ratio may not be the actual molecular formula. It could be the multiples of the empirical formula. Okay, so when we try to determine the structure of a new compound, when we have, say, you're doing a research in the laboratory there, and there's a naturally occurring product that has a very promising anti-tumor property, and you want to know its exact structure. And, well, the steps for new compound analysis there is that we have to make a sample, we have to know, when we study the sample, we have to know how there's quantitative science there. Okay? So you have to know how much sample you have, and you need to know the mass there. And then the second step, you want to decompose into you want to decompose the compound into its element form. This, we can do that in different ways there. An example that we gave you there, and you can decompose water into hydrogen gas and oxygen gas. You can have, if you have an organic compound, you can burn it and get it into carbon dioxide and water. Now we know where the carbon comes from, we know where the hydrogen comes from, and we can determine the amount of elements that is present in this fixed amount of new compound that we have there. And then we can find the mass for each of the elements in the known mass of the compound there. From there, we can calculate percent by mass. And if we know the mass, if we know which elements are involved, we can also determine the number of moles of each element. And then from there, we can determine the molar ratio. We can calculate an empirical formula. And we can also determine the molar mass of the compound. One of the instruments that we can use to determine the molar mass. We talked about the mass spectrometer when we talked about the isotopes there. So if you have a molecule, you subject that molecule into a high energy electron beam, you can knock off one of the electrons in that molecule, and making the molecule positively charged. And you can pass that positively charged particle through a magnetic field and electric field there. And then because of the charge and the path of that charged particle going through the magnetic field, and will bend towards a particular path. And you can project that onto a recorder or a detector where you can determine the mass of that particle. Now the mass of the particle is 1 electron less than the mass of the entire molecule. Now, electrons are much, much smaller, so we can ignore the mass of the electron there. The mass of the charged particle can be treated as the mass of the molar mass. It can be treated as the mass of the molecule itself, with 1 electron less. And the difference is not significant there. So using mass spectrometer, we can determine the molar mass. Now, if you know the empirical formula, and if you know the molar mass there, and you can determine what the molecular formula is. And we'll give you some examples about this particular process. Okay, so